Right, so as I was saying, let me just erase that. So this, then once you put everything and you have done the sum over the polarization vectors, what you end up with is that your radiation Hamiltonian will be given by half sum through k and lambda of omega k of a lambda k, a lambda dagger k, plus a lambda dagger a lambda. So there's a k there, the k, which will give you half h bar omega k to a lambda dagger, a lambda plus 1, which gives you something from h bar omega k sum through k of some n. Remember that n for the harmonic oscillator was a dagger, so this you're calling n plus that half there, just with that h bar omega. So this is one of the relation that I will be making use of in the lecture. The computation of this is too long, but this is the final answer. So then we can go back to the slides. So files. This is the lecture now. As I share the, go back to the slides. So this is the classical treatment of the radiation. So then the slides, so that was just a brief revision of the harmonic oscillator and also how it will generalize to the electromagnetic field. So let's start with what is in the slides. Right. So as I said previously, for the electromagnetic field interacting with a particle interacting with the electromagnetic field, the Hamiltonian, if you use minimal substitution, will be of the form E over C A. Now the vector potential is depending on the time, and we just want to manipulate this expression for the full Hamiltonian to find out what is V of t. So squared minus E phi of R and T. And then once we multiply, we now get H0. And as I said, H0 will just be this term P squared over 2M minus E phi of R and T plus E over 2M A dot P plus, because they don't really commute, the other term will be P dot A, but P is given by derivative. So this just, what I'm saying is that P is given by H bar over I of grad. So then this ends up giving you a term that will be going like I H bar divergence of A plus A squared over 2M T squared. For now, we are going to ignore terms that are of higher order in terms of the field. So this A squared we will ignore for now. Then in Coulomb gauge, if you remember from classical electrodynamics, div A is equals to 0 for Coulomb gauge, so that term goes away. So this means that we can read off what is the perturbation Hamiltonian. So it's just given by E over mc A of R and T plotted with P. So this is what we will be using. That's, I mean, if you want, this is what I've been calling V of T. So you then go ahead and you do what I did in the whiteboard slide. So then tell that do a mode expansion. This you know from classical electrodynamics. Right? Again, at this moment, 0, it's just a number. We have not yet made them into any operators. And this will just so if you do that mode expansion, so I've already explained why there's a cross term there and why this omega comes, because once you differentiate this d over dt, it's going to act at that point there, which will bring down this I omega. This one, you end up with a k cos e. So if you remember, I just spent like 10 minutes trying to compute things like this, lambda prime, k prime, and trying to rewrite them as k dot k prime, epsilon dot epsilon prime. And then the density for the electromagnetic field is given by the sum E squared plus B squared, because you can check that these vectors have the same magnitude. So this just gives you 2, 1 over 8 pi of E squared. Then you square that, so this will give you the A naught squared over omega squared. There's that 4 pi there, C squared sine squared K dot R minus, and then you take the average. The average of sine squared gives you a half. So this means that the energy per photon, so h bar omega over v, is what you've calculated once you have averaged out over this sine squared term. So this gives you the equation, delete, the equation that the energy per unit volume, which you can get from just averaging out unit time average of the sine squared, which gives you half. So this just gives you half omega squared A naught squared over pi C squared. Remember that we didn't really know that coefficient A0, and then from this relation, once you equate these two equations, then you can solve for what is A0. So then you get that A0 will just be given by h bar omega over v 2 omega squared pi C squared. And this was that thing that it's just that I put a 4, but it's the 4 pi C squared over v omega that I was putting in front of the mode expansion. So this term there. So A can be, so I've solved for what that A0 will be. So A can have a mode expansion like that. And then remember that V is given by, once I did that minimal substitution, I ended up with that V is given by A dot P. You already have the expression for A, so you just plotted everything. The thing that's a vector there will be that. So you end up with something like epsilon dot P. And now you can see that if you write everything, this gives you E to the EC square root 2 pi h bar C squared over omega V E I K dot R. from the previous slide, I call this thing V. Remember, I applied time-dependent perturbation theory to two cases. One was for when V was just a constant. The other one was when V was V of t was harmonic. So this gives you V dagger E plus V E minus I omega t. And this is of that form where now you can call that to be your V. Similarly, the other part then will be V dagger. And we have used time-dependent perturbation theory to compute those things. So we just make use of that expression. Yeah. We had already calculated this expression, just that there you had V dagger dot something. So then you're left with the. Now, if there is no radiation, so if A equals to 0, then these terms are not there. So this is that's 0. But that's problematic because we know that if you have a hydrogen atom with n greater than 2 in an excited state, it's possible for it to emit a photon spontaneously. So the classical treatment that we have done so far seems not to give us something that is correct, because we know that if atoms in excited states, maybe n equals to 3, they can decay, they can emit radiation, whereas what we've done so far with electromagnetic theory and then using time-dependent perturbation theory to compute this transition probabilities, that doesn't give us the answer that is in agreement with what we know experimentally. So then we look at how to quantize the electromagnetic field. So that's what we discuss next. So see. So we are going to use the fact that I just said that HR, that part where I did or tried to sketch as to how to do this, but HR is just the square, plus B squared. And then I showed that this is given by V over 8 pi C squared. The final expression, as I keep saying, it's very simple, but takes a while to, and I actually didn't do it in detail, so let me use K for now. K is pi squared. And in terms of creation and annihilation operators, just that I'm changing notation and using capital A. So this gives you a lambda K, a lambda K. This is the analog of writing H equals to A, let's say A dagger A as a half for the simple harmonic oscillator. Now, once we have that expression, then we can go back, right? Let's introduce operators. Delete. Like in the harmonic oscillator, you know that once you have A and B dagger, you've been doing this for the past 3 or 4 weeks. You know that X can be written as A plus A dagger with some number there, and similarly P. This you even did even last week when I gave you P to the 4, when we had to compute P to the 4 A dagger. Right? So we can do the same thing for the electromagnetic field. We introduce Q, just you know that P and Q are the same thing, so we introduce Q lambda K to be 1 over square root 4 pi C squared A lambda K dagger as A lambda K. These are vectors. This is the analog of, let me just emphasize this, this is the analog of this expression there. Right? And we do the same thing for P lambda K vector. This is I omega k over square root 4 pi c squared A just write it out. So A lambda coming with a negative sign, lambda k minus, but yeah, it's a set with a negative sign, lambda k. This is the analog of that expression there. Once you have this, then you come into the radiation Hamiltonian. So this gives you end up with some k and lambda of half p k squared p lambda k squared plus half omega k lambda squared q k lambda squared. Right. This is for the electromagnetic field. It's similar to what I started the lecture with, where you just had p squared over 2m plus s operators plus half m omega squared x squared. This is the analog of this expression for the Hamiltonian, but now for electromagnetic field. And these are just n independent harmonic oscillator type of equations. But at the moment, we have not really quantized. We were doing something similar for the electromagnetic field. We have not really quantized anything, because at the moment this is the same analog of that expression there. So we have not really promote anything into an operator. So that's what we found. So we need to find certain operators Q hat. Now I'll try to be precise, P hat and P prime, which will satisfy the, so I started this by X and P are the same thing. XP might have been 1, so we introduce this, but because we have these labels at the bottom, lambda 1, K1, theta, P lambda K2, this has to be someone, that one is written in terms of delta lambda, in terms of chronicle delta, and then delta K, K2. And so to connect operators, we introduce a lambda and operators that need, so lambda K given square root from K to is Q lambda K plus I over square root 2 h bar omega K P lambda K. I think the analog of that expression is A equals to, mess up, but maybe X minus IP in my notation. It's just that when I started the lecture, I had rescaled everything. So this thing there was what I was calling X. Similarly, this was what I was calling. It's just maybe without that I. And similarly, a dagger lambda K, this will give you square root omega K over 2h bar Q hat lambda K minus I over square root 2h bar omega K P lambda K. And then your HR will just be sum K. Actually, this is what I was trying to do in the whiteboard. It just becomes messy. But the final expression is that the expression for the Hamiltonian in terms of this creation and annihilation of operators given by h bar omega K n lambda k plus a half. This is the summary of what we have been trying to do. Where similar to the simple harmonic oscillator, this number operator lambda k is just the product a that a with lambda k, and the algebra that these operators then satisfy in the same way that I showed in the beginning. So remember that a was 1, but now for this system of an independent harmonic oscillator for the electromagnetic field, you get lambda 1 k1 theta a, maybe it was the other way, but a dagger lambda 2 k2. This commutator then gives you 1, but 1 written in terms of Kronecker delta, so you get delta lambda 1, lambda 2, delta k1, k2. This is the analog of that. And if you have operators of the same creation, the commutator between creation operators, this is 0. Similarly, the commutator between description, or if you have creation with creation, it's 0, and not creation, annihilation with annihilation is 0, creation with creation 1 1 lambda 2 k2. Again, this is 0. The only one that is non-vanishing is if you have a creation with an annihilation, then this types gives you 1. And in exactly the same thing that we did for the simple harmonic oscillator, you have things like, so remember that I tried motivating this expression, n factorial a dagger at 10 times on the vacuum. This gives you the n state. So similarly, the n lambda k, this state you can obtain by just put it there, because n with n gives you 1, so you ended up with cn squared was n. So cn was the square root of n, and then you repeated this process until you hit the vacuum. So this gives you n lambda k factorial a lambda k dagger acting n lambda k times on the vacuum. And then the operator, if you want, now I have to, the operator a lambda k acting on n lambda k. This is just a generalization of equations that you have been working with. N lambda k, this was one particle, so you end up with n lambda k minus 1. Similarly, a dagger lambda k n lambda k, this gives you square root n lambda k plus 1 and lambda k plus 1. And these are the expressions that we need to explain and calculate the transition probabilities and rates for spontaneous emission. So then maybe one final thing I should mention is that the eigenstates of what we call HR, these eigenstates are of the form n lambda 1 k1 and 2 lambda 2 k2, which are just products. So j n lambda j kj. Right. So let's go back and rewrite our. So let's start by rewriting the vector potential in terms of the creation and annihilation operators. So you get A of RT given by some K lambda square root 2 pi over omega K V A lambda K dagger E I K R minus omega T polarization vector lambda, so vector plus what we call Hermitian conjugate. But now these are, unlike in the classical treatment that we just did, where we just had, I think it was just only A0. These now are operators that can act on the vacuum. Once we have that, you know that V, so V of t is just the dot product of the momenta with that vector potential. You already have the expression for that, so you just dot and the product will only there. So this gives you E over m electron sum k lambda square root 2 pi h bar over omega k v k lambda k e I k dot r epsilon r dotted with a p plus the Hermitian conjugate if you want. So, and we have done these type of things. So we identify our V radiation, and now it's an operator because it's being written in terms of the creation and annihilation operators. This gives you E over mc square root 2 pi h bar over omega kv a k operator lambda e I k dot r epsilon dot p. And we have, remember that, as I keep saying, we have computed the ei omega t plus, it might be dagger the other way around. We went through a half of a lecture just deriving the transition probabilities for these types of potentials. So for the electromagnetic field, it means that we've already calculated this because this was quite general. Now we're just applying it where this V R is given by this with these operators there. So maybe let's say that the final state, which would be some tensor product, so let's say it's given by this, but now there's another thing which is from the electromagnetic field, which is n lambda k plus 1. Let's say that this is the vector. So when we compute the overlap, everything I'm saying will be included, is included in the next slide. So the overlap V with that operator V lambda k dagger. This gives you E over m square root 2 pi h bar over omega k psi final E minus I k dot r epsilon dot p psi final. And I think maybe, I think I've explained enough, so let's go through the slides and see. So I've explained that equation. Then let me just summarize what I've done. So in the whiteboard, what I tried to do was try to motivate that if you start with this e squared plus b squared, then you write them in terms of a. So maybe this might give you I omega, some expression for a. Similarly, the other one gave you k cos epsilon, some expression for a, maybe for 0. And then once you square everything and then you sum over and then you make use of the identity k cos epsilon, k cos epsilon, simplify this, do the integrals. So I kept writing things like d3 eik k minus k prime. These types of integrals give you some delta k prime. Or once you've done those, you end up with only a single sum over the case. Then with a delta a, then you introduced new operators, which were, you could try to write that and write it in terms of that. Then you promoted those Q's into operators, so which were written in terms of a, delta, and a, in terms of these operators. And then they satisfied this algebra that if you have a creation annihilation, this gave you a 1, but 1 written in terms of these Kronecker deltas. And if you have creation and creation, 0. Similarly, annihilation and annihilation operators give you 0. And this is the key result, that your Hamiltonian for radiation is just given by a set of n independent harmonic oscillators. And the end state can be obtained by just acting with these creation operators multiple times, and n lambda times. So this n lambda is just an integer, so it's 0, 1, 2, and so forth. Once it adds n lambda k times, then you get the state with n lambda k photons, and they satisfy similar relations that you get. So this is the analog of an, given by square root n minus 1. This is the analog of a dagger acting on n, gives you square root n plus 1, n plus 1. And you will see why you introduce those operators. Right. So I've explained that. This is the in the sense that once you have written your vector potential in terms of creation and annihilation operators, then the v of t given, this will just give you, it's just the dot product of a dot p. So the only and most of these things are not vectors except there. So you end up with two sums where you dot this with p, you dot that with p. And as I said, we have actually computed the transition probabilities for such an operator, these types. So I think if you look at earlier slides, we actually went through that. Just check the time. See when I started. Okay, so and then you can read off what this operator was, v and v dagger. And once you have those operators, then you are done, because we actually, as I keep saying, we actually have computed the transition probabilities for, we did it for the general potential of that form. So you just go back to that expression for, try to explain that. And you plug them there. So I was saying that if you started with some initial state with n photons, right, remember then the final one has lambda k. So you can consider the case where the final one has n plus 1. Right? So n lambda k goes into lambda k plus 1. I should emphasize that this is the final one. Final. And then you try to compute that overlap. So, and because these are just tensor product, we still have to compute. This side there, it's a tensor product of psi f with the state n lambda plus 1 k. We've done something similar where, if you remember, I think in the first lecture I was writing things like 0, 1 or 0, 0. Right? Maybe for the harmonic oscillator, you remember nx, y, and z. This was just the tensor product of nx, ny, and z. I'm doing this something similar here. And I think we have y, and I could separate stuff. So similarly, the a and a daggers do not act on that vector there, so they only act there. So you might end up, and v dagger is proportional to a dagger, so you end up with n lambda k plus 1, which is the final one, a lambda k dagger, and lambda k. And by now you know that once it adds that side, this gives you n plus 1, but with write everything out. So this gives you square root n lambda k plus 1. Then you get n lambda k plus 1 and lambda k plus 1, which is just, these things are normalized. If you put a 1 there, this is 1. So you're only left with that one there. And you can do the same thing for v. So v will be proportional to a. I think this is a typo. And once it adds there, remember that only once it adds on the vacuum does this give you 0, but on any other state it's not 0. So this just gives you square root n k minus 1 n minus 1. I'm just abusing notation. By n minus 1 there, I mean n lambda k minus 1. I'm just using the analog with the simple harmonic oscillator. This is 1. They are normalized, so we are left with that square root n k. And this is where things get interesting, because if you write everything in terms of these the operators, I should emphasize that these are now operators. Plug them there, right, and then square everything. So once you square this one, you get n lambda k, but the other one comes with n lambda k plus 1, right? And you can check that if there is no radiation equals to 0, this means that you are in the vacuum, in the ground state, where n lambda k equals to 0. So no radiation, no nothing. There's absolutely nothing. The system, so even though this term there, that n lambda k is 0, you still have a process of emission. This thing, the rate, transition rate for emission, it's not 0. And this is the whole point of this quantizing the electromagnetic field. Once you've quantized the electromagnetic field, you end up with these V Dagger operators. Once they start acting on your states, you that one of them might be creating, even though there is no electromagnetic field disturbing your system, the system can still emit, and this is the rate for spontaneous emission of a photon, even though there is no electromagnetic field. Now, if you go and you look at the expression that we wrote, there's this EIK dot R. So in the dipole expansion, so you can approximate this to be 1 plus or minus. I'll consider both emission and absorption at the same footing it.r plus dot dot dot. In the dipole expansion, we only keep the first term, dipole approximation. So you only look at that term. So this is just 1. Epsilon, as I keep saying, I think that two them, it's either 100 or 0111. So it's just a constant, so you can take it out of the overlap. And your left, it's outside, but you still have to dot this thing there. And you can check, let's consider maybe for 1 dimension, I'll generalize the result to higher dimension. So you have this P, but now you want to write it in terms of a commutator that will involve X and the amplitude polynomial to be free. So you can compute Px squared over 2m. So this gives you X Px over 2m plus Px over 2m X Px, and the commutator is Q P, which I wrote. This gives you 1, right? Or if you want, Q and X are the same variable, so this gives you 1. So this just gives you Px over 2m plus Px over 2m, which ends up giving you Px over m. Yeah, this thing that I think in the beginning of the lecture was I had rescaled everything, but it's IH bar. But if you, the commutator of X and P head of what I did, I think in the first 2 or 3 minutes of the lecture, that's 1, but this one gives you an IH bar, so you still have this. So this is coming from this ones we had computed. You can generalize that to 3 dimension. So instead of you having X, you have that R there. So this gives you that P vector. So this means that you know what this P, so this means P is given by commutator of R with H0. Just multiply everything by M over IH bar. Okay. I think there's a typo there. This has to be an R. So you end up having, in this dipole approximation, you end up having to dot the polarization vector dot psi R psi initial, and then you still have to square that. But this R, because try and write R in spherical coordinates. So let's say that you get R cos theta cos phi I. Remember that you are having to take overlaps, right? So it's better to rewrite this cos in terms of spherical harmonics. So write them in terms of y11, y10. And then you make use of this result, which, so the triple integral over the omega of 3 spherical harmonics, they are given by these Clebsch-Gordon coefficients. And there are selection rules for Clebsch-Gordon coefficients. So using those selection rules for the Clebsch-Gordon coefficients, we find that for these types of transitions, they are 0 unless this m prime. So if you look there, we wrote everything in terms of m was -1, 0, and 1, because we had this cos phi, cos theta, and those you can write in terms of y11, y10, and so forth. So this other m prime was -1, 0, or 1. So the selection rules are that the delta mi has to vary by -1, 1, or 0. and they have to have, again, the Clapeyron coefficients vanish unless this condition is satisfied. So then this means that Li minus Lf have to be odd. So this means that they have to have odd parities. So this means that you cannot go from 1s to 2s only for this type of dipole approximation. So you cannot go from 1s to 2s or 2p to 2p. There have to be different parities. So you can go from 1s to 2p. That one would be allowed, or maybe you go from 2p to 3s or something like that. Those types of transitions are allowed. Spontaneous emission. So for spontaneous emission, just certain things that we have to do. So you remember that this will give you d3p over 2 pi h bar cubed. You still have to do integrals over angular frequencies before c squared d omega. So if you want to find the total rate, you still have to integrate out over this the angular frequencies. So this is the total rate transmission. So let's start by looking at the omega if v d omega over 2 pi cubed d omega. But the point is that if you look at the expressions, they have a Dirac delta function. So if you want to do the integral over the omega, you still have to do dEi minus Ef minus h bar omega. This integral omega final I f squared omega. This integral you can go ahead and compute. And then the other thing that you will also have to use is that let's say dFi, dotted dipole moment dotted with you have to check what it's probably there in the lecture count that this gives you 2 over 3 dFi squared. So this means dWi to f e the emission. This gives you omega 3 over 3 pi c3 dFi with value d omega, and nothing then will be depending on the capital D omega. These are angular frequencies, these are just the angles. So then you can find what this rate will be for spontaneous emission. So this gives you 4 coming from the 4 pi. Once you integrate out the omega, you just get 4 pi, 4 which cancels this pi. So you're left only with 4 omega 3 over 3 h bar c3 dFi. Write out what this dFi is out explicitly. So you end up for spontaneous emission. I think this was the first computation done by Dirac, which is part of the reason why introduced things like Dirac is the one who introduced this creation annihilation operators, did the interaction picture that simplified all these computations to try and find the compute this transmission rate for spontaneous emission, which is a quantum mechanical effect, because classically it just works out to be 0. So for pi, then you have omega 3 over h bar c3 psi final r psi initial squared. So let me summarize what we find. So we find that this for spontaneous emission, W emission going from I to F, this gives you 4 omega 3 over 3 h bar c3 df. I think I had written out what dfi was, so it's just psi final r psi initial squared. This is the final result of this lecture, second final result of the lecture. And then the decay rates then will just be 1 over the sum of these things. So I think I've explained everything. Let's just check. Okay. And then the total power, okay, this I didn't explain. You just multiply the rate that you obtained by h bar omega. So this, then this is the one that I wanted, which is just this the decay rate, or the mean lifetime, will just be the inverse of one over these things that we computed. So as an example, says that consider a particle of charge q and mass m. It's moving in a one-dimensional harmonic oscillator. Find the rate, and this is what we calculated in this lecture, which is the rate of spontaneous emission. For transition from excited state N to the ground state, then obtain an estimate of for the rate calculated in A. Once you make use of approximate omega to be that in the particular sphere. So let's see. Then find the condition under which the dipole approximation is. So the dipole that you can check is, it's only valid. So you're approximating the exponential that was sitting inside this overlaps psi with lambda t. You approximated this to 1 plus k dot. These terms have to be small, so it means something like kx has to be smaller than 1. But I'll write down the precise condition. So the spontaneous rate of emission going from I to F, you just plug it into that formula that I derived. So you get 4 omega squared q squared over 3 h c3, but you still have to compute 0 as 0. But these are just simple harmonic oscillators that we have been working with since last year, and I think by now everyone can compute these types of overlaps. You still have to square that. So let's see, write everything in terms of harmonic oscillators. So this gives you h bar over 2m omega square rooted 0 a delta plus a n. I think everyone is happy with this. So a acting on n, h bar over 2m omega square root n plus 1, which is this one written there. Then you get delta 0 n plus 1 plus square root n delta n 0 n minus 1. And then you can form your own selection rules. So this delta there tells you that the only transitions that are allowed are from going from 0 to n equals to 1. N equals to n minus 1 equals to 0, n equals to 1. So this is the only one which is allowed. Right, I'm reading it from here. This one just tells you that n equals to minus 1, but the ground state is the lowest one, so that doesn't really play much of a role. So this means that W 1 to 0 spontaneous emission given by omega squared q squared over 3 h bar c3 0x, and I've just argued that the only non-vanishing selection rule will be when this is 1. squared. So like everything there, 4 omega squared q squared over 3 h bar c3 h bar over 2 omega squared. This is coming from, once you write this, comes from once you write this as creation and annihilation operator, you introduce that h bar over 2 omega, and then this simplifies into 2 over 3 omega naught squared q squared over mc3. So if you set q to be minus e, then you can just make use of that formula. So you have just saying that I've computed the rate for spontaneous emission in general for general charge, but now I'm just setting it to for an electron h bar c, write everything in terms of the fine structure constant h bar c, and then you just plug the numbers that were given. So I find that this gives me 2 alpha, write it 3 mc squared. This is mass of electron. This gives you 2. The rest is just plugging in these numbers. So alpha is 1 over 137, 197.33 MeV Fermi over 0.511 MeV. Multiply that by 9 times 10, 28 per second squared over 3 times 10 to the 8. These are just plug this into a calculator, you get 5.6 times 10 to the 5 per second. Then the lifetime is just the inverse of the rate of spontaneous emission. So I'm going from 1 to 0, which I calculated previously. Let me also write EMI. So this gives you 3 over 2 m squared over omega naught squared e squared, giving me 1.5 times 10 to the 5 second, which is not second squared, 0.1. I'll write everything out in the slides, 10 to the minus 5. And C, which was this question, it's valid when kx it's way smaller than 1. This means that, and we can find what is kx. So kx is just omega naught over c square root v over 2m omega naught is square root h bar omega naught over 2m c squared. This has to be way smaller than 1. So that leads you to the fact, so it's only valid if h bar omega is smaller than 2m c squared. So h bar omega naught is given by h bars, just write the volume 197.33 MeV. And the condition is, oh, okay, I think this is the condition. I'll type the solution to this exercise and then I'll upload these slides. For now, I'll just upload the video. Okay, I'll end the lecture here.